starts now. So I want to get started. We'll start by the now. Topological spin dynamics. Yes.
Thanks a lot for the introduction. Of course, thanks to the organizers for putting together this very nice meeting in this exciting place. I've never been here. And yeah, it looks very nice. Sorry about being late, but I was best man at the wedding on Monday, so just started to surprise. Okay. Anyway, so I'm going to talk about topological spin dynamics and just a quick rundown of what you can expect in the next 30 to 32 minutes or so. Very briefly, skyrmions, you all know what skyrmions are. It's a good thing about such a meeting. I don't have to introduce these spin structures to you. A little bit about the stability that we've been investigating using some multi-scale modeling. And then the main part of the talk will be the dynamics due to spin orbit torques of skyrmions, the skyrmion racetrack, and the skyrmion Hall effect. And then a few words about spin orbit torques and anti-ferromagnets with the outlook of them also possibly manipulating skyrmions. So let's start. Well, there are all these applications that we always motivate our work with. And since I don't think we have any contact monitors here, we can say, you know, we motivate our work with that. I'll never invest in a company that promises a skyrmion racetrack as a device that will make it into my hard drive. Okay, I've sold all my shares in IBM, so I don't invest in it. Okay, but there's also logic and possible sensing. And just for the students here, a word of caution. This is an interesting fact. So Stuart Perkins once told me that there's more than $100 million invested in the racetrack memory device. But there's not a single dollar made. Now, also a few $1 million went into spin structure logic, such as domain ball logic, and about €1 million were invested in the domain ball-based sensor. And that thing actually now makes a turnover of $50 million. So sometimes the less cool devices actually make money, and the very cool devices make good money. All right. So, but all what you need for these devices to work is that you have to make them stable. So you need to have long-term information retention by stable spin structures. You need to be able to manipulate these spin structures with high efficiency and speed. And ultimately, you don't want to have any stray fields to have maximum package density. And for that, you don't use that. So I'm going to actually talk about these challenges. And so first off, stability. Well, I really don't want to go into a lot of detail. You all know what the Topological interaction is. And here I'm going to talk exclusively about interfacial EMI. So I'll combine a heavy metal layer, which belongs to orbit interaction, and a ferromagnet. And then at the interface, you have the coupling of two ferromagnetic elements by the orbit of metal layer here, and this generation EMI, which favors perpendicular alignment rather than the direct Heisenberg coupling, which favors co-link. And that, the combination, then leads to spin canting, and it leads to not spin canting in an arbitrary direction, but it has a set chirality. So here we're going back to our topology columns. And the great advantage of that is that for such a narrow domain wall, this domain wall here is energetically favorable because the spin clockwise, whereas this one here is energetically unfavorable because the spin is counterclockwise going from left to right. And so this means you have chiral domain walls, and if you crank up the EMI, you can have these skyrmions. Alright, so that's all I wanted to tell you because you all know this anyway. But the very important experimental thing is how to characterize them. Now, the Jarzynski-Maria interaction is something, at least for me, something new. I've only known it for about 5 years or so. And so to characterize the EMI, a number of different mechanisms and measurement procedures have been developed. And I just want to show you some of these disadvantages and advantages, because at the moment we're a little bit at a loss of how we can determine the EMI with high fidelity. So we developed this domain imaging technique whereby looking at the stripe domain width, you can determine the EMI. So this was first finding this paper here, and there's a very nice model by Peach's group. And from that you can deduce, if you know other parameters, the EMI. An alternative approach was developed by Bosu Han, also my group. And here looked at the switching of the triangles, and then due to the EMI, you get some spin canting at the edge of such a triangle, which then leads to shift of the hysteresis loop, a little bit like changed by a central redshift, you can determine the DMI. Now there are other methods such as PLS or these, generally the asymmetry of the spin dispersion, bubble expansion, domain motion, and so on. Now let's look at these different. The outcome. Well, the first thing that we want to measure by using different methods is to see how does the DMI scale with thickness. And what we see very nicely is if you plot it as 1 over the thickness, then you have a linear scaling. So really it's an interfacial effect. If you make the ferromagnet thicker, the effective DMI goes down. All good. But now if you want to go quantitative and you compare the different methods, where you see also bubble expansion, then we see, for instance, by comparing these domain width and the bubble expansion, we get quite good agreement. So when we compare, for instance, domain motion versus spin wave dispersion relation, we actually get a factor 3 or so difference. So this, you're not the only ones who have seen that. And the interesting thing is that this is just for all the community. I think this paper here has a lot of exciting information, but we have a lot of trouble publishing it because we get a difference in the DMI between Gonzalez plane. This paper is, it's kind of also nice, but we just had agreement. But I would say scientifically, this paper is much more important, but we have to go through about 5 journals until we finally got it published. So sometimes I think the publishing disagreement is more important than publishing agreement. But the take-home message here is different methods to measure the DMI don't all seem to measure the DMI. And that is something I think we as a community really have to figure out. And at the moment, I also don't know what is the best method. Probably spin structure imaging is rather robust, but I think all the other methods have drawbacks. And you need to take care when you analyze the DMI measurement, effective DMI that you measure on the system.
It's all room temperature experiments?
It's all room temperature experiments, all on the same samples. But for instance, if you do like domain motion, you might have current damping. If you have BLS, then you have asymmetric and isotropy. I mean, they're all like advantages, disadvantages. But I think the important message here is don't trust the paper which says I measured the DMI. Only trust the paper saying I measured the DMI using this method. And I think within a method, if you use the same method, then you can explain, then you can compare different systems. But you cannot compare many systems, you cannot compare 2 different systems measured with 2 different. Well, what is nice about DMI is it's a subtle effect. You can tune it by the 2p5 electron time translation at the interface. And there are also very surprising things, for instance, going from cobalt 20 iron 60 boron 20 to cobalt 40 iron 40 boron 20, and normally not changing anything else, changes the DMI by a factor 5. So this was shown in this paper. So it's a very subtle effect that is extremely sensitive to the interface composition. Okay, this is all my for the theoreticians might sound very technical, but I think it's very important that if you want to compare results from the literature, that you know what method they use. Now, let's come to skyrmion. So if you have enough DMI, whatever you measure, if you have enough DMI, you can stabilize skyrmions. And for the sake of this talk, I call the skyrmion a spin structure, which you can map onto the sphere. So magnetization on the outside of that spin structure has to be parallel, and it has to be anti-parallel to magnetization in the center, and then everything else happens somewhere in between. So this then leads to different types of spin structures depending on the DMI. Hedgehog skyrmion, chiral skyrmion, then what I call a bubble skyrmion, where it's primarily the polar interaction of the DMI, which stabilizes it, and then you can not only have these n=1 skyrmions, where the binding number here at least is 1, but you can also have spin structures which look rather similar, but have a different binding number. This one has n=0, it's a topologically trivial spin structure. It doesn't look so different, but still, it has a very different topology. This has very important implications for the stability. We now compare the stability of these 2 spin structures, then we see that when we apply a field to kill them, this spin structure here changes the movement, the skyrmion shrinks a little bit, but stays a skyrmion. Whereas this here, because it's a topologically trivial spin structure, with a very small field can be destroyed because there is no energy barrier to stabilize this. So I think this is very important to know that these 3 spin structures have topology that's distinct from the uniform state, which means that you cannot continuously are what I call topologically not necessarily protected, but stabilized. Now, we actually looked at that using a multi-scale model, and you need a multi-scale model because at the, for instance, the center for vortex, also the main ball, you have large magnetization gradients which cannot be appropriately modeled using the magnetic model. So you use here the Heisenberg spin model. However, we cannot use the Heisenberg spin model for everything because it becomes computationally expensive. And then we looked at how to kill a skyrmion. So this was the, I actually asked my PhD student if he wants to call his PhD how to kill a skyrmion, but he had a nicer title in the end. But essentially, this is what he did. He found out different ways to kill a skyrmion. So one is that you can apply a field which is sufficiently strong to annihilate the skyrmion by simply shrinking it to 0 diameter. And you can also use nucleation of Bloch line that actually then goes from n equals 1, and you nucleate Bloch line, which is minus 1, so the total winding number becomes 0, and then you can manipulate the skyrmion as well. What is important to note here is that there's never an infinite stability for skyrmion. Since we're on a lattice, there's only a finite energy barrier. And this finite energy barrier depends on the magnetic property. So more DMI can make a larger energy barrier. However, even in a continuum model, there is no unlimited stability because you can always shrink the skyrmion to 0 diameter. This was nicely shown in this paper by Felix Bittner, former PhD student of mine now. Alright, so this is just a little bit on the theory how to kill skyrmions. Now let's do an experiment. So you see that from Jeff Beach, so I don't have to go into a lot of detail. We can make these skyrmions stable at room temperature, and we have skyrmion lattices in these confined geometries. By confining them in the geometry, we can say that's a 3x3 or a 4x4 lattice in the same distance, because we of course have to be commensurate with its radius. The size of the skyrmion can be tuned as well, and it turns out that always people somehow magically have the size of the skyrmion, which they can measure with their technique. So Axel was the first to show that optically you can measure these micrometer-sized skyrmions. We looked also together with his colleagues here in France at using X-ray microscopy at skyrmions of 200 nanometers, and if you go to the STM people or he only needs 11 spins for a skyrmion. So you can have a huge range of different sizes of these skyrmions. And so we're going to come here look at skyrmions which are somewhere between 30 nanometers and 300. So the first thing we wanted to look is at single skyrmion dynamics, just the relaxation dynamics. For that we apply a field in order to stabilize one or a few skyrmions. And then it was predicted a long time ago that the skyrmions actually show a rather complex relaxation dynamics when we put them all center, for instance, here in this. So we excite the skyrmion, and then it relaxes back to its original position on this hypersurface trajectory. That is a direct consequence of the topology. So in order to identify that we are in n=1 skyrmion, we need to observe such a dynamics. And then my PhD student, Felix Bittner, he did the experiment. So he went to a state where you have 2 skyrmions. So the skyrmion just has magnetization up on the inside and magnetization down around it. We excite it with a bipolar field pulse. And then we look at this one skyrmion here, which we excite somewhere off center. And then from this position here, it could go back to its original position very easily. However, due to this topology, it does actually this little bit here at the end, which is the sign of this topology of as well. So you see that in the movie that the skyrmion, after it's being excited, in the end makes a little wiggle, and you can fit that wiggle in order to extract things like the mass of the skyrmion, which obviously in my system can be rather large, but the important thing is if n equals 1 and n equals 1 is topologically stabilized. So now we got our n equals 1 skyrmion, let's do something with it, let's manipulate. So what we do for the manipulation to get high efficiency and speed is we use orbitors. So the 2 origins of the spin orbitors that we're looking at is the spin Hall angle. The spin Hall angle converts a longitudinal charge current into a transverse spin current. So you see here the spin right electrons are being scattered to the top interface. They then diffuse across the interface into the ferromagnet, and then by the transfer angle momentum, they manipulate this ferromagnet and exert 2 torques that give like angles and just be like control. Now, in addition to this bulk effect, which also an interface effect, which is the inverse of the binding effect, and that leads to non-equilibrium spin density for electrons flowing at the interface, and these then act by exchange on the magnetization and manipulation. So now we have these two effects, which both exert field-like and damping-like torque, and together they can exert a very strong torque. So in the lab we find effectively something like a transfer of 10 H bar to each electron on average for the current flowing across the skyrmion.
Which effect is stronger?
Hi, very good question. We wrote a proposal to find this out, and I think in retrospective I was lucky that it got granted because I think it's a super difficult question. Because both effects exert both torques, and you can play a little bit by changing the thickness of the different layers and try to understand. However, changing the thickness changes the interface, so changing one thing changes everything. And so in the end, I think we don't know. I think there are good indications that in many of these systems, the Hall effect is the dominant part. But then I learned from Kläui that also there can be limitations to the Hall effect, and then again. Okay, anyway, we have these two effects, and in the end, what we as experimentalists want that they exert a lot of torque on our skyrmion. And to characterize the system, we have a very nice collaboration with people like Mathias and where you can measure this effective torque resulting in the effective spin Hall angle by using a terahertz excitation, here, and we find that, okay, platinum has a large spin Hall angle, tungsten has a lot of palladium. It's quite well known. However, now the nice thing is we can combine now opposite tungsten and platinum because they have opposite spin Hall angle. If we plug platinum below the cobalt and then tungsten above, they add up. Because platinum below and tungsten above, opposite spin Hall angle, the action on the ferromagnet is the same. So what we do is we look at platinum, cobalt, and tantalum, platinum, cobalt, and tungsten because they give us effects. And this is then when we set out to work with Jim Beach and see if we can make a skyrmion racetrack. So we had regular students, as you move through this picture before we did the experiment, and said like that's what he wants to see. So then we went to the synchrotron and hey no, we see 4 skyrmions. And then we went to actually look at some kind of displacement. And we did that, and it kind of looks okay, they're rolling back and forth. However, if you look closely, we start with 5 skyrmions, and after a little bit of injecting current back and forth, we end up with about 2 skyrmions. So we lost 60% of our data. So some sort of technology partner was not terribly impressed, but we wanted to check where does that come from. So we went back to theory, we did theory, and in theory everything is perfect. We have 3 skyrmions, we're happily moving completely synchronously in our wire, depending on the direction of the current, and to the left or to the right. And you can also see that the trajectory of this skyrmion is not along the current flow, but under some angle, the so-called skyrmion Hall angle, which I'll mention in more detail later. You also see that the skyrmion is repelled from the edge, and therefore then it moves along the edge, and then the switch of the current moves back to the center. But of course, in the experiment, it's not what is happening. One of the skyrmions does what we expect, one of the skyrmions doesn't move at all, and one of the skyrmions needs it later. So here we have 2 skyrmions playing. Okay, so you see that the 2 skyrmions chasing each other, and in the end, one skyrmion beats the other. But that's not the important bit. The important bit is that you see the first skyrmion before it's being eaten is pinned. Now it's pinned, and the other one comes and eats it. And that's a very important observation. We only observed that one skyrmion is the other skyrmion, but one skyrmion was pinned. So this tells you something: pinning is bad. Pinning essentially lowers the energy barrier to be eaten. And here the DMI in the system should be big enough that only inputs one skyrmions are stable. But locally, if you have a local reduction of the DMI, then you can locally change that binding number and the skyrmions converge. So the message is we need better materials which have less pinning. So that's what we set out to do. Well, of course, we first read all the nice theory papers that say skyrmions don't care about defects. Here we have a theory paper that you have defects in the wire and they shouldn't care. Here you see skyrmions that go around the edge roughness, they shouldn't care, but they do care. So we start with lots of skyrmins, and after a few injections, we end up with very few skyrmins. So then we did a lot of materials engineering, and this is for the students. It's really tough work to engineer good materials, but it's super important. And then we saw that other people have the same problems. You see here that also skyrmins can be irregularly spaced, so there are some pinning sides. We published here a paper where we see one skyrmin does move, one skyrmin does move on the tungsten-based stack, and also on this iridium-based stack where we have very small skyrmins, we see virtually all pinning very reproducible displacement. So most of the stacks that are out there in the literature have very strong pinning. Then we went out to change materials and change growth parameters, and after a while, and a lot of hard work, so this sounds very easy, but this was like 110 stacks later, we have a stack where we see that the skyrmins move at least 50 times back and forth very happily. So then we went back to Samsung and told them it works 50 times. And then they said, well, we would like 10 billion times. So I went back to the student and told them we can do it 10 billion times. And then the student said the PhD is too short. So then we need to be smarter. So rather than doing single pulse, measure, we went to the synchrotron to measure dynamically. Here the velocities that we get are quite nice, 150%. So here at the synchrotron, we now then did a real-time image where this is actually an average over 10 billion repetitions. And the fact that you see that these 5 skyrmions move back and forth means that they do this 10 billion times repeatedly. If once the skyrmion got out of sync with the pulse, you would not be able to see the contrast. And because the question always comes, about 80% of the skyrmions in this material show this reproducibility. 20% are either thin or we don't see the dynamic meaning they don't do something. Now, if you plot the velocity and the pulse shape, you see that the velocities track the pulse shape rather well, so that it's low inertia and it's reproducible. However, if you look at the current direction and the skyrmion motion direction, you see it's also under some angle. We plot the current flowing right left, the skyrmions all move in the same direction, but under this so-called skyrmion Hall. This was predicted a long time ago using a rigid skyrmion model that the skyrmion Hall angle depends on size. However, what was not predicted and was found both by Axel's group and our group is that the skyrmion Hall angle actually changes with velocity over time. And there are different theoretical models. One you'll hear about in the next talk. And the one that I'm going to put forward here is based on the skyrmion deformation together with the field-like torque that can explain this change in the skyrmion Hall angle velocity. And we've measured it with different temperatures, and we see it's rather constant, not dependent. So the question is, why does the skyrmion deform? And then, well, there are all these theory works on the eigenmodes. You see there are breathing modes and more complex modes that can lead to deformation when you excite the system, and this can explain how exactly happens. Now, if you come from Germany, then you see multiple skyrmions then moving synchronously, anything must be loaded. So we want to load the multi-day racetrack. One day is not enough. So this is a European skyrmion which can drive on the left lane, and you can also change lanes and drive on the right lane. And if you want to actually implement something like that, for instance, a reconfigure logic, that would then allow you to move skyrmions on very complex trajectories. And this is something which is a huge advantage over the domain model. You can never do this with the domain model. Look at the skyrmion working. However, it's a problem with the skyrmion Hall, because if you have your skyrmion which moves towards one edge, you cannot move it across between different lanes very easily. So what can we do? Well, it was already predicted some time ago, for instance, in this right here, that you can simply combine 2 skyrmions in a synthetic anti-ferromagnet. And then if one skyrmion wants to go to the right edge and one skyrmion wants to go to the left edge, and now we couple them, then they actually move together. Because if one wants to go right, one wants to go to the left, but together they have to go to the center because they cancel out, or the 2 things cancel out, and then they move perfectly in the center of the wire, and we can move them around corners as shown here. And this would be used for this complex new logic device. And I think fundamentally, this is the main advantage of skyrmions over domain modes. Domain modes are great, and I think for a normal racetrack, I think there is limited advantages. But I think something like this would never be feasible with a domain mode. But with a skyrmion, you can do this, and skyrmions are really complex trajectories. So these are synthetic antiferromagnets. We made some of these. It's using more flexible multilayers, and we see huge torques, and it's usual to apply things faster than us. You already saw it years ago. So this is all fine, but it's very tough to engineer a system to have spin orbit torques, perpendicular and sort of the arc-Y interaction, and DMI. So we are kind of struggling with that to get a system that shows skyrmion and also a system that can. However, we might just take the next step and say, like, don't worry about synthetic antiferromagnets, we want real antiferromagnets. Because of course, a real antiferromagnet, the coupling between subatoms is huge, like 100 Tesla, not like here it's only a few billion Tesla, which means that the skyrmion Hall angle could actually be still a problem if you crank up the current density, because this coupling strength of 10 million Tesla would still allow the two skyrmions to rip apart if we try. This is strong enough, but in a real antiferromagnet intrinsic one, this would not be a problem. So let's do antiferromagnets and see if we can make antiferromagnets spin orbitals. So this was predicted some time ago by Mathias and LANL-SkyrmionWorkshop group that in manganese to gold, you can switch the L vector by 90 degrees by injecting current along perpendicular direction. Obviously, if you have two subatoms like this and this, so turn 180 degrees, nothing happens, but there's a difference between this and this. And this what you can do. This 90 degree switching is what was predicted. Material was first observed in copper arsenide, and the work was primarily done by two PhD students, and it's the growth of materials really done from northern last science in my group, which I showed you how many years because it was quite tough to get the material to grow. And then we made these samples, and again, sounds very easy, but if you look here, the first paper was 2015, and we now have our paper on archive that actually works. So it's quite a tough experiment. We have such a cross, and in this cross we can apply current along two perpendicular direction. And then indeed we see switching that, depending on the current direction, the magnetization of the L vector moves by 90 degrees, and it looks rather similar to what was observed in copper manganese ice. It's highly nonlinear. You see changing by 20% the current density changes the switching hugely, and we can even switch across the rho XY0, which means that we switch more than 50% of the L vector. So more than 50% of our switches. So now we can switch it and we can read it out by a large AMR. Now the question is, can we use skyrmions in that? We're trying at the moment. At the moment we don't know yet, but hopefully in 6 months or so we'll be able to show you at least the main structures and see if we can have skyrmions. All right, that's it. My time's up. This is the most important slide. So this is my group. In particular, I'd like to acknowledge Martin Sauer and Martin Möller and Jörg Lakoff, and staff scientists with me, and many former group members that have worked on that. We have very good collaboration with the group of Jeff Peach, Mathias, Fischer, and Stefan Eisenberg. There's a lot of imaging done. For theory, we work with Kläui and Mathias group. And for the synchrotron-based measurement, this really is all able to get great synchrotron staff, such as Marcus Weigand and Inizio, and we work with other people on materials and to keep the contact funding. And so to summarize, the DMI can stabilize spin structures to define topology. Be careful about what you read in terms of DMI measurements. The scary dynamics depends on the topology. Spin orbitals can lead to very spin manipulation. You can make a racetrack initially not so successful, later more successful. And in antiferromagnet, we can get real spin orbitals. Skyrmions we shall see for the papers. And with that, thank you for your attention.
Thank you, Mathias, for a nice talk. Open for questions and comments. Yes.
We showed your racetrack with the 10 billion repetitions of SkyrmionWorkshop. The skyrmions are pretty close together, and I'm wondering why they are not interacting in a way.
Okay, I mean, of course, there is topological, so they might interact. We're just discussing, this is not a skyrmion lattice, so the distance between the skyrmions is larger than it is in the natural lattice configuration. Essentially, we cannot switch on and switch off the interaction. So what we see sometimes that skyrmions cluster together and move together very rigidly, so they're must be some attractive short-term potential interaction. That's something we're trying to find out at the moment by playing Gilead with the skyrmion. So we shoot skyrmion onto another skyrmion and we see how they get scattered. But it's an extremely difficult experiment. So we're trying to measure the scattering factor of the skyrmion and another skyrmion.
I'm not 100% sure you told us about the current density and the speed of these experiments of this very good student who did this very nice things. 40 minutes, 100 minutes.
So this is similar to the main ball. Same physics, spin-orbit talks for the main balls of skyrmions, similar velocities, similar current densities. Just one word of warning, everyone says skyrmions are great because they can move at ultra low current density. That is true, but then they also move at ultra low speeds. And there's no free lunch. If you don't put more H bars in, not many H bars will change and will be very slow.
Yes.
So when you expected the max from the dynamics, do you have to worry about that the skyrmion is moving in very isotropic potential?
Absolutely. I mean, we did a fit, and I didn't show that here, we did a fit to this trajectory, and it could be fitted with, assuming a spherical potential. We did 3 or 4 of these, and I think what is important to note here that the potential that leads to the resetting is actually not the edge of the disk, but it's a local defect that pins the potential. And I think, if you look at the total distance it travels, it's very small. So I think it's not unreasonable that it's spherical, but let's say we cannot exclude that you could also have like very harmonic potentials and things like that.
You probably have some interaction with the things coming on that they are.
That's enough. I mean, okay, of course you cannot exclude it, but the distance is not, compared to the excitation, the distance is rather large. And the distance is like more than 10 times the distance it moves. So I don't think that the straight rate will change a lot. I agree that this is a point that one needs to take into account. And I think if you want to make a big impact, find a way to characterize the pinning size of our materials. Then you can start.
Many colleagues like you and others use spider science. And I think this is probably the only way to connect to web technology. But in order to understand better about the pinning, the maximum speed, it would have been possible to do MBE growth at least once.
We have it. I can tell you the main problem with MBE growth is it works very well for a very small sample, and then you have a terrace of 100 nanometers, and then you have one misfit dislocation, which generates a huge pinning size. So if you do MBE, you have to do it like Roland Wiesenberger, and only characterize one really single crystalline area. But he only looks at 5 by 10 nanometers or something. Yes, there we can grow MBE and perfect. But to grow it on a micron size, it's very tough.
Final question.
Actually, two. So when materials work well,
Yeah.
what is it?
So
Then
yeah.
you make it, you make say 50 devices to the all work pretty well.
Yeah. So the material is platinum coated iron ore MgO. One of the big improvements we did is the growth of the coated iron ore into the perfectly amorphous layer. So you can all find it in this paper. And if we make 50 samples, then if we use a commercial spotter machine, so we have a single commercial spotter machine, which makes 8-inch wafers with less than 1% variation, and it's an amazing machine where, for instance, the age of the targets is taken into account. So it changes the parameters with the age of the targets. And then it makes perfectly reproducible samples. On our normal spotter machines, we always have to run a test where we run through a list of sample parameters to get the same operating conditions again. On this commercial machine, it's fantastic, but it's very expensive.
What color composition is it?
It's 20-60-20. We also have 40-40-20, but has less DMI.
All right, with that, we conclude the talk. Thank you very much. Next talk is by Charles Whitehart from Australia, the fluctuations in mind. She's going to